Hi everybody, welcome back to the Feynman technique. So today we're going to try to derive a closed form expression for gamma of 2n plus 1 over 2. In other words, basically the gamma of all the half integers. So the gamma evaluated at things like 1/2, 3/2, -1/2, -3/2, etc. All right. And we're going to be using the integral definition of the gamma function. So gamma of z is equal to this. All right. And this is just kind of a recurrence relationship. The gamma of z plus 1 is always equal to z times gamma z. And that can be shown using integration by parts on our definition of the gamma function. And it's also just a standard factorial recurrence. You'll recall this property. This is always true, and since gamma and factorials are easily relatable, we can just extend it to this relationship right here. Okay. All right. So let's see. If we take gamma of n plus 1/2, well, we can write that as n minus 1/2 times gamma of n minus 1/2. All right. We can extend that further, and we see if we keep doing that over and over again, the following pattern emerges, and we end up with just gamma of 1/2 at the very end of the recursion. And look what happens here. Let's focus basically on these two terms right here. The progression on the top goes 1, 3, the next one would be 5, then 7, then 9. So it goes like that, and the bottom always has is just a factor of 2. And then let's just state that these are algebraically equivalent. All right, and now we can just write gamma of n plus 1/2 like this. This 2n minus 1 double factorial, some of you might not be familiar with the double factorial notation. What that means is we start at whatever number this is, and the double factorial notation means that instead of adding, for instance, 5 times 4 times 3 times 2, double factorial means wherever you start, you keep subtracting 2 from the previous term. So this, if our n was, say, 5, the term in here would be 9. 9 double factorial would be 9 times 7 times 5 times 3, etc. So hopefully you can see where this comes from. And now, to fully figure this out, let's figure out what gamma of 1/2 is. All right, we can find gamma of 1/2 by plugging 1/2 into our gamma function formula right here. So gamma of 1/2 is equal to this. All right, what are we going to do now? Let's let t equal x squared. dt is 2x dx. So our gamma of 1/2 is now just equal to this. And that's going to simplify nicely. Here's some of that algebra. And finally, we end up with gamma 1/2 being equal to this. All right. And that is something, that's the Gaussian integral. Now on this channel, we've derived a generalized form of this. We know the value of this function when we have the parameter a inserted in there. We derived this about a month back on this channel using differentiation under the integral sign. We determined that this was true. Now this is the general form of our specific case where a is equal to 1. So gamma of 1/2 is just equal to square root of pi, because it's 2 times square root of pi over 2, which is just square root of pi. So we have gamma 1/2 is square root of pi. We plug that back into our formula, and this is exactly our formula right here. Now I did do one more step. I showed how to I showed the conversion of 2n minus 1 factorial. I converted it to a combination of powers of 2 and just regular factorials. So in the next step, I basically rewrote that. These two expressions, this and this, are equivalent. And I'm going to leave it to you to, if you're interested, to just kind of teach yourself why that's true. 2n minus 1 double factorial over 2 to the n simplifies to this. But anyway, guys, there's your formula for half gammas, and this is it. This is the formula. So you can find, for instance, if we wanted to know what gamma of 1/2 is, we simply plug in 0, and we get square root of pi. If we want gamma of 5/2, well, we would just plug in n is equal to 2, and let's see, if n is equal to 2, we get, let's see, 4 factorial, which is 24 over 4. Now that's a little bit too complicated to do in my head. But anyway, that's the formula. Hope you enjoyed that, and we'll see you next time.